This video is for Module 2, Part 2, and will include the helper versus hinder case study. Okay, let's go ahead and get started. In the helper versus hinder case study, infants were presented one of two toys. One of the toys was considered the helper toy, and the other toy was considered the hinderer toy. There is a short video that describes this study. So I'll go ahead and pause here so that you can watch that video. Okay, so what is the research question? The research question for this case study is, do 10-month-old infants prefer the helper toy over the hinder toy? So that's the goal of the investigation, is to determine whether or not the infants prefer the helper toy. There are some important elements of this study that will be talked about later. For example, the color, shape, and order of the toys were varied and balanced across the 16 infants. That was done to prevent confounding, and again, we'll mention that at the end. For the study outcome, there were 14 out of the total of 16 infants that ended up picking the helper toy. So at least from the initial, that's most of those 10-month-old infants ended up picking the helper toy. So there probably is a preference, but we'll go ahead and conduct a statistical hypothesis test to verify that. Okay, so real quickly, the two different toys. The first one was the helper toy, which in this screenshot here is the gray square that is trying to help the red circle up that little hill. The other toy is the hinderer toy, and that hinderer toy here is the yellow triangle that's trying to push the red toy back down the hill. These two toys were then presented to the child on a tray. You can see we have the gray square and the yellow triangle. And what they observed, or what the outcome from the study was, which toy did the child tend to go to first? The helper toy, as this child did, or was there preference towards the hinderer toy? So before jumping in and doing our statistical investigation, I will let you answer this first question here. What is the scope of inference for this study? That is, to whom do the study outcomes apply? And they gave us information about that in the methods section of their article, which I have presented here. So go ahead and hit pause and answer that first question. Okay, in this study, each child was asked to select either the helper toy or the hinderer toy. The reference distribution will be constructed under the situation of no preference. So a child will have a 1 out of 2 chance here of selecting the helper toy over the hinderer toy when there is no preference. So this is going to be another 50-50 situation. So let's go ahead and write out the alternative hypothesis on each of the two that I have provided here. I've given you the null hypothesis, and I want you to write out the alternative hypothesis using words and then also using symbols. And I'll go ahead and do that with you here. So remember that the research question, if we go back up to the top and look at the research question was, do 10-month-old infants prefer the helper toy over the hinderer toy? The research question is what goes into the alternative hypothesis. Okay, so the null hypothesis here is 10-month-old infants have no preference. The alternative hypothesis is that 10-month-old infants have a preference for the helper toy. If we want to write that in terms of our parameter, then we're going to say the probability of selecting the helper toy is greater than 50%. So if that probability is indeed greater than 50%, then these 10-month-old infants are going to have a preference for the helper toy. What would the alternative hypothesis look like if we were to write it using symbols? Well, quite simply, the parameter value is denoted by pi. So the alternative hypothesis, would look something like this here, where pi is just greater than 50%. We're going to see later that this is a right-tailed test. Okay, it's going to be a right-tailed test because we are interested in whether or not that parameter value is greater than 50%. All right, let's just look at the visual depiction of the simulation model, or of the reference distribution, There were a total of 16 10-month-old infants that participated in the study. So our number line is going to go from 0 up to 16. If most of the kids pick the helper toy, then there's going to be a preference towards the helper toy. So the right end of this distribution is of interest. The expected outcome is simply going to be 8 here. It's just going to be 16 times 1/2. So the expected outcome under no preference is going to be at 8. This reference distribution is just halfway up the number line. So again, that helps determine where the expected value is. The reference distribution is going to be built under the no preference situation. The study outcome here is 14. So that sits up on that right side. So that's the outcome from the study, is 14 kids ended up picking the helper toy over the Hinder toy. I will skip over the table that describes each of those values. I will just mention that the side that we care about is determined by the research question. So the research question here is, do 10-month-old infants prefer the helper toy over the Hinder toy? So that's what determines whether or not you're on the right side or the left side or both sides, is the research question. Some students like to take a shortcut, which is they just look at what side the study outcome is on. Okay, so here it's on the right side, and then make the decision that, oh, it must be right-tailed. That's not how we determine the tail of the distribution. The tail of the distribution is determined by the research question, not where the study outcome is at. Okay, so let's start putting these pieces together for the various elements of a test. The first step here is a research question, which we've stated. We need to take that research question and put it into a testable hypothesis. Need to identify what the parameter is, and then we can rewrite that hypothesis test using that parameter as is stated here. Need to identify what type of test this is, which is a right-tailed, as we've discussed. The observed outcome was 14 10-month-old infants selected the helper toy. What outcomes do I need to compute the p-value? So I need to answer that question before I can compute the p-value. So we discussed that previously in the previous part. I need to identify what values are as extreme or more extreme that would provide support for the research question. My study outcome was 14. We go back up here to the visual. My study outcome was 14, so the values that I would need in computing the p-value are going to be values at 14, values at 15, and values at 16. So the p-value is going to be the proportion of dots that are at 14 or higher. Now we're going to go ahead and use the reference distribution app to compute that p-value. It's going to be a little bit more convenient because I can get the number of repeated outcomes up fairly high and do that easily. So my reference distribution, my sample here is provided here. I'm going to set up the probability of heads here at 50%. Again, that's probability of success if it's a non-50-50 example. So this app is set up for coin tossing. So that's why at 50% here it reads probability of heads and then number of tosses. So more generally, this is the probability of success, or the pi value, which is just 50%. Number of tosses is the number of trials, or the sample size. That's going to be 16. And then I've specified the number of repetitions, or the number of repeated outcomes, to be 5,000. If I select as extreme as 14, that's my study outcome here, what the app is going to do is compute the proportion of dots that are at 14, 15, or 16. So that is going to go ahead and compute the proportion of dots that are to the right of 14. There were 11 dots that were to the right of 14 out of a total of 5,000. So I went ahead and put 5,000 dots on this graph. So the p-value from my sample here is going to be 0.0022. Okay, what I'd like you to do is just hit pause and go ahead and set up your own reference distribution using the reference distribution app. And I will do the same as well here. Okay, so when I did it in my first instance, it looked like I had 11 out of the 5,000 that were at 14 or higher, and that gave me a p-value of 0.0022. When I did it a second time here, it looks like I got 12 out of 5,000, which gave me a p-value of 0.0024. And this again was using a total of 5,000 repeated outcomes. So go ahead and use your value that you got here for your p-value and answer the following questions down below. So I'll go ahead and do that with my p-value here. So my p-value is 0.0024. To make my statistical decision, I need to check whether or not that p-value is less than 0.05. So 0.0024 here is indeed less than 0.05. So I do have enough evidence for the research question. So which statement is the correct statistical decision for your test? It's going to be statement A for me. And finally, writing a conclusion. Remember, when we're writing a conclusion, we want to do that so a non-statistician can understand what your findings were from your investigation. And that conclusion has 3 parts. I'll go ahead and just show you these 3 parts here. The first part is the decision. So there is enough statistical evidence. The second part the second part is just a restatement of your research question, which I'm just going to go up here and copy and paste that in. So now my conclusion is there is enough statistical evidence to say that 10-month-old infants prefer the helper toy over the Hinder toy. And then the last component is to include what your level of evidence was, which for us is just going to be the p-value for now. So my p-value again from my reference distribution was 0.0024. So there's the 3 different parts of the conclusion. You don't need to identify those 3 different parts in the conclusion. I'm just doing that so that you can see those various parts. So if I take those parts out, that's what your conclusion would look like. Okay, just some final comments. The number of repetitions or number of repeated outcomes that you use should not influence the p-value too much. Okay, so you're going to have a p-value, or at least you should have a p-value kind of close to the one that I've obtained here. This is especially true because I asked you to do this reference distribution with 5,000 simulated outcomes. So this reference distribution has settled down quite a bit. Even on the edges, it's settled down quite a bit. Of course, the app does allow me to obtain many, many more. So here I obtained 20,000, but you can see that the p-value doesn't change very much. Now my p-value is 0.0023 instead of 0.0024 that I had up above. Okay, let's talk finally about the confounding aspect in this study, or the lack thereof. So one of the statements that was made in the description of the problem was the following: the color, shape, and order of the toys were varied and balanced out among the 16 infants. So let us suppose that that was not the case. So suppose that all children received exactly the same setup for the experiment. Suppose that all children were presented in a situation in which the helper toy was given the green square and the hinderer toy was always the yellow triangle. Now suppose 14 infants picked the helper toy, which for everybody was the gray square. So in that case, we're going to have a concern, and in particular, we can't be certain that they picked the gray square because it was a helper toy, or maybe kids just don't like yellow, or maybe kids don't like triangles, or maybe if the gray square was always placed on the right side of that tray, and most of us are right-handed, maybe that's why they picked that, and not because it was the helper toy. So when they did this study, they varied or mixed up the color, shape, and order of the toys for each of the 16 different infants. So maybe sometimes the red circle was actually the helper toy. So they mixed up all the different colors and all the different shapes. In doing so, they're going to prevent confounding in this study. The design process, this last paragraph here, the design process to prevent confounding for this study is different than the breastfed and bottle-fed example. In the breastfed and bottle-fed example, a matched paired process was used. And in that process, we wanted to keep things as similar as possible. Here in the helper-hinder case study, we want to vary those situations as much as possible to prevent confounding. So again, in the helper-hinder, we wanted to vary the experimental setup for each infant, but in the breastfed bottle-fed situation or study, we wanted to use a matched paired design to keep things as similar as possible. So the moral of the story here is the process by which the experiment is conducted must be taken into consideration when attempting to prevent the adverse effect of confounding in a study. So the methods that we use to prevent confounding are going to vary from different study or from study to study. And those methods, okay, what we call that the design aspect of the study. Okay, that does it for Module 2, Part 2.